Hello! Today we continue our study of rotational motion and talk about how angular and linear velocities and accelerations are related to each other. So let's start with velocities. First, let's remember that we have two types of velocity. The first is linear velocity, which will describe the translational motion of the body, and as we remember, this is the ratio of the traveled to the amount of time that it's traveled. We also introduced in the last lesson the concept of angular velocity, which determines how fast a given body rotates, and is defined by the ratio of the angular displacement to the time over which the displacement is also made. So now the question arises as to what the relationship between these two quantities is. Let us look closely at this relationship. If we look at the same time interval delta t and divide these two expressions by each other to get rid of the given time, we get the ratio of linear velocity to angular velocity, just like linear displacement to angular displacement, Now let's remember that the length of the arc that rests on this angle will be related to the magnitude of this angle by a known relationship. It's the product of the angle and the radius of the circle on which this movement is actually taking place. And we divide that by this angle. So we get that. The angular displacement in this case is reduced, and the ratio of linear velocity to angular velocity is equal to the radius of the circle. That's the interesting fact we've got here. Or let's write it down as a relationship between linear and angular velocity in this form. We will often meet this formula in rotational motion, and I advise you to remember it because here very often we have to pass from linear parameters to angular ones. Now, in terms of acceleration, in this case, we need to remember that acceleration is the rapidity of change in velocity. Speed, as we understand it, is a vector quantity. So it has a direction and it also has a numerical value. To explain acceleration, let's consider the motion of some object along the arc of a circle, and at each point on this circle we can take two of these points. The velocity will be tangential to its trajectory. The tangent, as we remember, is at an angle of 90 degrees to the radius, and we can draw a radius to each point a different radius, a vector. And perpendicular to that radius is the velocity vector. So even if the velocity is constant in modulus, in direction we can see that it will change continuously, and this shows that the velocity vector in this case does not remain constant. And this indicates that there will be a certain amount of acceleration. And this is where you and I meet the first type of acceleration, which is responsible for the direction of velocity in curvilinear motion. This is the center of rapid acceleration. This acceleration is defined by the ratio of the square of the velocity to the radius of the circle on which the body is rotating. That's the first formula you and I need to familiarize ourselves with. And then, of course, you can substitute the linear velocity for the linear velocity we already know to get the second formula, which is that defines the relationship between acceleration, centripetal acceleration, and angular velocity. Thus, we have obtained two definitions for the centripetal acceleration. And now let's consider the situation where not only the direction of velocity, but also the modulus of velocity. So motion on a circle can also be either equideceleration or equideceleration, so the velocity can change in magnitude. Then, of course, you and I would have to say that not only the linear velocity will change, but also the angular velocity will change. So let's say that if the linear velocity remains constant, then the angular velocity also remains constant. And thus it turns out that if we have a certain acceleration responsible for the change in linear velocity, then there will be a certain acceleration responsible for the change in angular velocity. For the change in linear velocity, we have a so-called tangential acceleration, which will determine the rapidity of change in the value of this velocity. Accordingly, here we introduce a new type of acceleration called angular acceleration, and it determines the rapidity of change in angular velocity. As we can see, the formulas are almost duplicates of each other. We just change the linear parameters to angular parameters. It's very simple. Well, and in order to now link these quantities, let's also divide these two expressions into each other. So we get that. The ratio of tangential acceleration to angular is the ratio of the change in linear velocity to the change in angular velocity. Well, as you and I have guessed, we can also now use the formula that relates linear and angular velocity to each other and substitute in this expression. What we get is delta omega times the radius and divide by delta omega. It is clear that only the velocity changes, the radius remains constant, so we've written the expression in this form. Well, and thus, reducing the change in angular velocity, we obtain the relationship between the two accelerations, linear and angular. This formula will also come in handy for us in the future, because in general we will use it when we're describing equal variable motion. So in this way, today we have received the connection between linear velocities. We have considered what is the acceleration in rotational motion. Now we've got two new types of acceleration, centripetal and tangential. And we also remembered that there is also angular acceleration, which will also determine the rapidity of change of angular velocity. All these quantities will be used in practice. See you in our next lessons. Goodbye.